Welcome to the Diagnostic Lab. We're jumping right into this explainer today to demystify a truly crucial component in all of modern electronics, the capacitor. We're going to explore exactly how these ingenious little devices store, hold, and manipulate electrical energy using nothing but the invisible architecture of electric fields. Think about your smartphone or your laptop for a second. You'll actually find arrays of physical capacitors inside almost everything you own. But you might be wondering, why do we even need them when we already have batteries? Well, batteries are great, for sure, but they supply energy at a relatively modest, slow rate. So what happens when you need a massive, high-speed energy discharge? Something like the blinding burst of a camera flash? That is exactly the problem our lab is going to solve today, and it's all thanks to the physics of capacitance. Here's our roadmap for today. We'll start with the blueprint of capacitance, then move into holographic capacitor geometries, wiring the grid, energizing the field, and finally, the dielectric upgrade. All right, let's dive into part one, the blueprint of capacitance.
The sheer elegance of this fundamental formula is striking. Q equals C times V. Basically, the magnitude of charge, Q, stored on the capacitor's plates is directly tied to the potential difference, V, and the device's capacitance, C. Now, we measure capacitance in a unit called the farad, named after the legendary Michael Faraday. 1 farad equals 1 coulomb per volt. But here's the catch. A single farad is an absolutely massive unit of measurement. Why? Because a single coulomb represents a staggering amount of charge, literally way more than tiny electronic components could ever handle safely. So in the real world, you're mostly going to be dealing with microfarads or picofarads.
Moving right along to Section 2, holographic capacitor geometries.
In our lab, we follow a really strict standard operating procedure. Whenever we design a new geometric build for a capacitor, we calculate its capacitance using 4 rigid steps. First, we just assume a charge Q has been placed on the plates. Second, we use Gauss's law to link that enclosed charge to the surrounding electric field, E. Third, we integrate that field to evaluate the potential difference, V. And finally, we just calculate C by dividing Q by V. It's basically a perfect, foolproof diagnostic loop.
And what's wild is that whether we're dealing with flat parallel plates, a long cylindrical coaxial cable, or even concentric spheres, there is a glaring pattern in the math. Capacitance relies entirely on geometrical factors. It's all about the surface area of the plates and the separation distance between them. Tweak the physical geometry and you fundamentally change the capacitance.
Okay, let's look at Section 3, wiring the grid.
When we wire capacitors in parallel, we're essentially creating one giant capacitor plate. The overall capacitance just adds up perfectly. Simple, right? But when we wire them in series, one after the other in a line, they behave fundamentally differently. The equivalent capacitance is actually calculated inversely. This means that adding more capacitors in a series circuit actually decreases the overall system capacitance.
To keep all of this straight, we use a really brilliant memory trick, par-V and series Q. Par-V reminds us that capacitors wired in parallel share the exact same voltage. Series Q tells us that capacitors wired in series share the exact same charge, Q. Lock those two little phrases into your mind, and I promise you will never wire grid incorrectly again. But now we kind of have to pause and ask a fundamental question. Once our grid is perfectly wired up and completely pumped full of charge, where is all this energy actually stored? Like, where does it physically sit? To answer that, we have to pivot from the hardware itself to the invisible physics happening in the empty gap between the plates. Let's figure that out in Section 4, energizing the field. Think about the work required by a battery to push electrons onto those plates and charge the capacitor. That effort doesn't just vanish, it builds up as stored potential energy. That total stored energy, U, is intimately tied to both the charge squared divided by twice the capacitance, or 1/2 the capacitance times the voltage squared. But, that's just the math. The physical reality of what's happening is even cooler. The crucial point here is this concept of energy density. This reveals a totally mind-bending reality. The potential energy doesn't just sit on the metal plates. It physically resides within the invisible vectors of the electric field itself. Anywhere an electric field exists in the universe, it has an energy density, a specific amount of potential energy locked inside every single unit of volume of that seemingly empty space. Which brings us to our final stop, Section 5, the dielectric upgrade. Way back in 1837, Michael Faraday realized something amazing.
If you take a standard capacitor and completely fill the empty vacuum gap between the plates with an insulating material, something like mineral oil, plastic, or glass, it acts as a massive system power-up. We call this material a dielectric, and it multiplies the original capacitance by a specific factor known as the dielectric constant, or kappa.
To really put this into perspective, let's look at the number 310. That happens to be the dielectric constant of a material called strontium titaniate. By simply slipping a piece of strontium titaniate between the plates of our capacitor, we instantly multiply its ability to store charge by 310 times. And we do that without changing the physical size of the plates at all. The sheer scale of this upgrade is incredible, but how does slipping a piece of material in there actually work?
Well, we have to zoom all the way down to the atomic level to understand it. When we insert a polar dielectric, the applied electric field forces the random molecules in the material to align, kind of like a bunch of little compass needles. Once aligned, these atoms actually create their own mini electric field pointing in the exact opposite direction of our main field. This internal tug-of-war weakens the overall net electric field, which drops the potential difference and ultimately allows the battery to push significantly more charge onto the plates.
Now, because the dielectric changes the very nature of the electric field, our ultimate mathematical tool, Gauss's law, has to adapt. When a dielectric is present, we simply multiply the standard permittivity constant by our new dielectric constant, kappa. This elegantly allows us to account for all those tiny shifting atomic charges without losing the beauty and simplicity of the original equation.
And with that, our lab diagnostic is complete. You now understand the blueprints, the geometry, the wiring, the invisible energy fields, and the incredible atomic upgrades that make capacitors work. So I want to leave you with this thought. Look around the room you're sitting in right now. Can you imagine the millions of microscopic, invisible electric fields locked inside the dielectrics of your phone, your computer, and your appliances, silently holding on to energy, just waiting for the exact millisecond you need it? It really makes you look at the circuitry hidden in your own home in a whole new light, doesn't it? Thanks for joining me on this explainer, and keep questioning the invisible physics all around you.